On the morning of the 22nd of December, 1964, a single aircraft lifted off the runway at Air Force Plant 42 in Palmdale, California. Its pilot, Lockheed test pilot Robert Gilliland, advanced the throttles on its two Pratt & Whitney J58 engines and felt something no human being had felt before in a production aircraft, the equivalent of two locomotives accelerating him skyward. The aircraft climbed away from the Mojave Desert at a rate that defied what engineers on the ground believed was possible. It reached an altitude of 50,000 feet in minutes. It was capable of flying faster than a rifle bullet. Its airframe skin would heat to temperatures exceeding 300 degrees Celsius at cruise speed, hot enough to cook meat. When Gilliland landed and climbed out of the cockpit, the aircraft's titanium skin was still too hot to touch with a bare hand. The aircraft was the SR-71 Blackbird. When Soviet intelligence analysts in Moscow received their first technical briefs on the SR-71's declared performance specifications in 1966, several of them concluded the figures were a deliberate fabrication. Not because the Soviets doubted American engineering. They had watched American engineering produce the B-52, the Polaris missile, the nuclear carrier Enterprise. They respected it. They concluded the figures were fake because the specifications described something that their own mathematics told them could not exist. Not yet. Not with any materials or manufacturing processes they knew of. A titanium aircraft that cruised at Mach 3.2 sustained skin temperatures of over 300 degrees Celsius for hours at a time and remained structurally sound was not just beyond Soviet capability. By their calculations, it was beyond the physical properties of the metals required to build it. They were wrong. But the reason they were wrong is not a story about genius. It is a story about a problem that Lockheed's Skunk Works division solved between 1958 and 1964 that most of the aerospace world did not know existed, and that the Soviets, when they finally understood it, could not solve for another 20 years. This is a story about titanium, and about what happens when you try to build something that the universe of available manufacturing knowledge does not yet know how to make. The problem nobody had solved. To understand why the SR-71 was considered impossible, you have to understand what happens to metal at Mach 3. At 3 times the speed of sound, friction with the atmosphere heats the leading edges of an aircraft's wings to temperatures that would soften aluminum into something approaching putty. Aluminum, the material that had built every high-performance Western aircraft since the Second World War, the P-51, the B-17, the F-86, simply ceased to be structurally useful above roughly 130 degrees Celsius. Steel was stronger, but 3 times heavier than aluminum, and weight was the enemy of every performance parameter that mattered. The aircraft that the CIA and Air Force wanted, the successor to the U-2, something that could overfly the Soviet Union at speeds no surface-to-air missile could track, had to be built from a material that in 1958 barely existed in usable industrial quantities. It had to be built from titanium. Titanium is the 9th most abundant element in the Earth's crust. It is stronger than steel and 45% lighter. It retains its structural properties at temperatures that reduce aluminum to a liquid. On paper, it was the perfect aerospace material. In practice, in 1958, working with titanium at production scale was something the American aerospace industry had almost no experience doing. The metal is extraordinarily reactive when hot. It ignites in pure nitrogen. It absorbs hydrogen from humid air and becomes brittle. Standard high-speed steel cutting tools wore down to nothing when machined against it. The coolants used in conventional metalworking contaminated it. chlorinated tap water, the kind that came out of faucets in every factory in the United States, caused stress corrosion cracking in titanium alloy parts that would not show up for months. When Lockheed's Skunk Works program manager, Kelly Johnson, received the contract to build what would become the SR-71's predecessor, the A-12, the team's early estimate was that 92% of the aircraft structure would have to be titanium. The Skunk Works had perhaps a dozen engineers with any titanium experience. The American titanium industry could not yet roll sheet stock to the tolerances required. The fasteners needed did not exist. The tools needed did not exist. The manufacturing knowledge, in the industrial sense, the accumulated craft understanding, the jigs, the gauges, the heat treatment protocols, the quality control methods, did not exist. Kelly Johnson had been given a contract to build an aircraft out of a material that the industrial world did not yet know how to manufacture. He had approximately 4 years to figure it out.
The Skunk Works and the gauge. What followed at Lockheed's facility in Burbank, California between 1958 and 1962 was one of the least documented industrial revolutions in American history, classified at the highest levels, known to perhaps 300 people, and not declassified in any meaningful detail for decades. It was, in its structure, remarkably similar to what John Hall had done at Harper's Ferry Armory between 1819 and 1824, when he developed the first truly interchangeable parts. It was the patient, methodical, often maddening work of establishing manufacturing standards where none existed. The Skunk Works engineers began by destroying things deliberately. They manufactured titanium parts using every conventional method available and then tested the parts to failure, cataloging every failure mode. Cadmium-plated steel tools caused titanium to become brittle through galvanic corrosion. Stamped lot numbers written in ordinary marking pen ink caused stress cracking along the ink lines weeks after application. Parts stored in boxes in the California summer heat warped in ways that were not detectable until final assembly. Cadmium, chlorine, fluorine, chemicals present in dozens of ordinary industrial processes and materials turned out to be silent contaminants that degraded titanium in ways that showed up not on the production floor, but 6 months later at altitude, under load, when a panel distorted or a fastener failed. Each failure built the knowledge. Each failure eliminated one more variable from the manufacturing environment. The Skunk Works, by a process of systematic elimination that resembled scientific method as much as it resembled industrial engineering, began constructing a controlled manufacturing world inside the Burbank facility. New tooling was designed specifically for titanium. Carbide cutters, special drill geometries, new grinding wheel formulations. Temperature-controlled storage was built. New cleaning processes were written from scratch. Every chemical that touched titanium was cataloged and tested. Water used in the facility was analyzed and filtered. Ordinary tap water, it was discovered, contained enough dissolved chlorine to begin the stress corrosion process. The fasteners presented their own subproblem. An aircraft of the SR-71's complexity required hundreds of thousands of fasteners. Standard steel fasteners would corrode against titanium through galvanic reaction. The Skunk Works needed titanium fasteners, which meant they needed a fastener supplier capable of producing titanium fasteners to tolerances that the fastener industry had never been asked to achieve. They found a small supplier and essentially taught that supplier how to manufacture to the required standard, writing the quality specifications themselves, sending engineers to the supplier's facility, rejecting shipments that did not pass gauge. It was the same process William Knudsen had imposed on the American defense industry in 1940. If the part did not pass, it went back. The supplier was not asked to adjust. The supplier was asked to improve or be replaced. By 1961, Skunk Works had created something that had not existed before: a coherent, repeatable, documented system for manufacturing precision components from titanium alloy at production scale. Not perfectly. There were failures throughout the A-12 and early SR-71 programs. Components that cracked, panels that did not fit, airframes that had to be substantially rebuilt. But the knowledge was accumulating, institutionalizing, becoming process rather than individual expertise. It was being written into procedures, gauges, checklists, supplier qualification standards. It was becoming, in the language Kelly Johnson used, a system. The enemy's dilemma. Soviet intelligence had been watching American high-altitude reconnaissance programs since the U-2 began its overflights in 1956. When Francis Gary Powers was shot down over Sverdlovsk in May of 1960, Soviet engineers had the opportunity to examine a high-performance American aircraft in unusual detail. What they found was sophisticated but comprehensible. The U-2 was built from aluminum and steel, using manufacturing techniques the Soviet aerospace industry understood and in some areas matched. The gap between American and Soviet capability in the domain of conventional airframe manufacturing was not comfortable, but it was not unbridgeable. The SR-71 was different in kind. When Soviet intelligence analysts assembled what they knew about the SR-71 program in the mid-1960s, the performance figures the Americans had released publicly, the radar signatures that had been tracked, the contrails observed at extreme altitude over the Pacific, the picture that emerged did not fit their engineering framework. Their aerodynamicists could model Mach 3.2 flight. Their thermodynamicists could calculate what skin temperatures that speed generated. Their materials engineers could then look at those temperatures and state with confidence what the structural requirements of a sustained flight vehicle at those conditions would demand. And their conclusion was that the materials required to meet those demands, titanium alloy processed and fabricated to the tolerances the performance figures implied, could not be reliably produced by any manufacturing system they knew of, including, by significant extension, any manufacturing system the Americans were known to have. The Soviet titanium industry in the 1960s was, in some respects, larger than the American one. The Soviet Union had substantial titanium ore deposits in Ukraine and the Kola Peninsula, and Soviet military planners had recognized titanium's strategic importance earlier than their American counterparts. Soviet submarines, particularly the Project 661 Papa class and later the Project 705 Alpha class, used titanium pressure hulls, a manufacturing achievement that genuinely impressed Western naval analysts when it became known. The Soviets could work titanium. They could weld it, roll it, forge it. What they could not do, what they had not developed the industrial system to do, was machine it and assemble it to the tolerances that a Mach 3 airframe demanded. The difference was not in the raw metal. It was in what the Skunk Works had spent 4 years building. The procedures, the tooling, the quality control systems, the supplier qualification standards, the accumulated institutional knowledge of how titanium behaved under every condition it would encounter, from the raw stock to the finished aircraft. It was, again, the gauge tradition. It was Harper's Ferry. It was the difference between a country that had mastered the system of interchangeable manufacturing and a country that had skilled craftsmen working with micrometers and files. The Soviet engineers who doubted the SR-71 specifications were not fools. Their skepticism was a perfectly rational inference from what their own manufacturing system could achieve. They looked at what they knew how to build and concluded that the SR-71, as described, was beyond what any industrial system currently could build. They were right about the second part. They were wrong about the first.
because they did not know what the Skunk Works had built in Burbank between 1958 and 1962.
The irony of raw materials. There is an additional layer to this story that was not publicly known for decades, and that, when it emerged, struck many historians as almost too perfectly ironic to be real. The titanium from which the SR-71 was built came in significant part from the Soviet Union.
In the late 1950s and early 1960s, the American titanium industry could not produce sufficient quantities of the specific alloy grades the Skunk Works required. Domestic suppliers were stretched, their production capacity limited, their stock often failing to meet specification. The CIA, through a network of third-country front companies and intermediaries, shell corporations in Europe, purchasing agents in neutral countries, brokers in the global commodities markets, arranged to acquire Soviet titanium ore and processed titanium sponge. The Soviets, hungry for hard currency and unable to identify the end use of the material they were selling, supplied it. The KGB, for all its penetration of Western intelligence networks, did not connect the titanium purchases to the Black aircraft program at Lockheed until years later.
The metal that the Soviet Union sold to earn foreign currency was being machined in a classified facility in the California desert into an aircraft designed to overfly the Soviet Union beyond the reach of any Soviet weapon. Kelly Johnson knew. He found it grimly amusing. He reportedly told a colleague that they were building the Foxes from the henhouse's own timber. The MiG that could never catch it. Between 1968 and 1989, the SR-71 flew 3,551 operational sorties. It was never shot down. It was never caught. Soviet, North Korean, Vietnamese, Libyan, and Cuban air defense systems tracked it, fired at it, scrambled interceptors against it, and achieved nothing. The MiG-25 Foxbat, built specifically as a high-altitude, high-speed interceptor, the Soviet answer to the threat posed by aircraft exactly like the SR-71, could reach Mach 2.8 in emergency conditions, but doing so burned through its fuel in minutes and risked destroying its engines. It could not sustain the speeds required to close the distance to an SR-71 cruising at Mach 3.2 at 85,000 feet. The interceptor pilots who tried described the experience in terms that became something of a legend in Cold War aviation circles. You could see the Blackbird on radar. You could calculate its course. You could get airborne, climb to your service ceiling, push your throttles to maximum, and watch the blip on your scope pull steadily away from you. It did not maneuver. It did not take evasive action. It simply flew faster than you could follow. And it had been doing so continuously for however long it had been airborne before you scrambled, and it would continue doing so long after you had to turn back toward your base to avoid flaming out your engines. What those pilots were experiencing was not simply an aircraft that was faster than theirs. They were experiencing the operational consequence of a manufacturing system that had solved a problem their country's industrial base had not solved. The MiG-25 was a remarkable aircraft. It was built from nickel-steel alloy because the Soviet aerospace industry could work nickel steel to the tolerances a high-performance interceptor required. Titanium, in the quantities and at the fabrication standards that would have allowed a lighter, faster aircraft, was beyond what Soviet production methods could reliably deliver. The MiG-25 was what it was because of what Soviet manufacturing could make. The SR-71 was what it was because of what the Skunk Works had taught American manufacturing to make. Speed was the visible difference. Manufacturing capability was the underlying one.
What the Skunk Works actually built? In the end, the SR-71 program produced 32 aircraft over its production run. 12 were lost to accidents, a loss rate that,
for an aircraft operating at the absolute edge of what material science and human physiology permitted was considered acceptable. None were lost to enemy action. But the more consequential product of the Skunk Works between 1958 and 1964 was not the aircraft. It was the process. The documented, transferable, institutionalized system for working titanium at production scale. The supplier qualification standards, the tooling designs, the cleaning procedures, the quality control methods that allowed an inspector to determine quickly and reliably whether a titanium component met specification. That knowledge, that inheritance, flowed forward into every American high-performance aircraft program that followed. The F-117 Nighthawk was built on it. The B-2 Spirit incorporated it. The F-22 Raptor, whose airframe is 39% titanium by weight, could not have been built without it. Every generation of knowledge built on the one before. The way John Hall's work at Harper's Ferry built on Eli Whitney's concept. The way Henry Ford's assembly line at Highland Park built on the Springfield Armory's gauge tradition.
The Soviets eventually solved the titanium manufacturing problem, partially, unevenly, over decades. Their Alpha-class submarine, commissioned in the 1970s, demonstrated genuine mastery of titanium welding at scale. Their aircraft industry made progress, but the gap in institutional knowledge, in the deep, accumulated craft of working the material under controlled conditions to aerospace tolerances, was never fully closed during the Cold War. It was the same gap that had separated German manufacturing from American manufacturing in 1944. It was not a gap in intelligence or ambition or national resources. It was a gap in the inheritance of systematic precision manufacturing, in the tradition that ran from Harper's Ferry to Springfield to Highland Park to Burbank, California.
The part that did not need you. There is a coda to this story that belongs to 1976. In September of that year, a Soviet Air Force pilot named Viktor Belenko defected, landing his MiG-25 Foxbat at Hakodate Airport in northern Japan and requesting political asylum. The aircraft was disassembled, exhaustively examined by American and Japanese engineers, and returned to the Soviet Union in pieces 6 weeks later. The examination produced a detailed intelligence assessment of Soviet aerospace manufacturing that confirmed much of what the SR-71 program had implied about the gap in manufacturing capability. The MiG-25's airframe was largely nickel-steel alloy. Its electronics used vacuum tubes in several systems, where American aircraft had used transistors for a decade. Its engines were powerful, but operating at thermal limits that gave them service lives measured in hours, rather than the hundreds of hours standard in comparable Western power plants.
The American engineers who examined the Foxbat were not contemptuous of it. They respected it as a genuine engineering achievement, a formidable weapon system built by an industry working at the edge of its capability. But they recognized, in examining how its parts fit together, the hand-fitting marks on mating surfaces, the evidence of individual adjustment in the assembly of components that should have been interchangeable, the signature of a manufacturing culture that had never fully made the transition from the craftsman's file to the engineer's gauge. A senior Lockheed engineer who reviewed the MiG-25 assessment report made a quiet observation to his colleagues. He said that a Soviet mechanic opening the engine bay of a crashed MiG-25 in the field, reaching for the torque wrench to pull a component that needed replacement, was doing something fundamentally different from what an American mechanic did with the same task on an American aircraft. The American mechanic reached for the replacement part, knowing it would drop in. He did not need his file. He did not need his micrometer. He did not need to spend the better part of a day dressing the mating surfaces to make the new components seat correctly against the old structure. He just bolted it down. That difference, a replacement component that drops in versus one that must be hand-fitted, is the difference that the SR-71 program made visible at strategic scale. It is the difference that determined which country could sustain operational tempo in a conflict, which country's aircraft could be turned around faster between sorties, which country's maintenance crews could keep more aircraft in the air at any given moment, not because of the aircraft's design, because of the manufacturing system that made the part.
The SR-71 was the fastest air-breathing aircraft ever built. Its Mach 3.2 cruise speed remains unmatched in sustained operational flight by any aircraft that has followed it. Soviet engineers were right to be astonished by it, right to suspect, initially, that the numbers were fabricated. The aircraft was genuinely beyond what the world's engineering knowledge could produce in 1958. By 1964, it was not.
The difference was 6 years of methodical, documented, institutional learning. 6 years of destroying titanium parts in every possible way and writing down what happened. 6 years of building gauges and writing specifications and qualifying suppliers and throwing out the parts that did not pass. 6 years of extending a tradition of precision manufacturing that had begun with a breech-loading rifle in 1819 and had been moving continuously in one direction ever since.